Okay, it starts. Okay, I think I give you enough equations, right? Many equations. So with different problems, we use different equations. Okay, we did example 5.4. Okay, that's the isothermal conditions for that boundary layer flow, right? Isothermal. So in other words, that's the constant temperature on the wall, okay, on the surface. So we use Reynolds number, Nusselt number, okay, average Nusselt number to kind of find out the total heat transfer through the surface with a convection fluid, right? The flow goes through it with convection heat transfer. That's 5.4, okay. I have a couple of people in the waiting room. Hold on, let me admit everybody. Okay, so let me turn to my screen. Okay. So last time we actually talked about the iso heat flux condition, right? Iso heat flux. So there's a constant heat flux going through the surface to the wall or to the fluid. Okay. Let me keep the waiting room up. Yeah. Okay. So we have an equation for what? Let's do a review. We have a local heat transfer, local Nusselt number. Okay. Local heat transfer coefficient in order to calculate the local heat transfer rate, which is the heat flux, right? Then we have an overall heat transfer coefficient, overall Nusselt number, okay, to calculate the overall heat transfer Q, okay. And then it's average. It's not overall. Yeah, overall heat transfer rate. Okay, and also the average. If you divide it by area, become average heat flux. Okay, it should be the same as it's iso heat flux condition. So it will be the same as the Q prime initial input, the heat flux, right? Then based on that, we can calculate the average wall temperature. That's the goal. Okay, because for iso heat flux condition, you don't know the wall temperature. Wall temperature changes, right? So for the overall heat transfer coefficient, overall Nusselt number is used to calculate actually the average temperature. Okay, it's average Nusselt number and average heat transfer coefficient. Okay. Okay, so these are the difference between isothermal and iso heat flux condition. Okay. We also presented the equation for Prandtl number outside of this range. Okay, be careful. The notes here is outside this range. Okay, hold on. I think I might. Okay, outside this range. Outside this range, you have a equation like this. Okay, for the isothermal, for the iso heat flux condition, basically is the changing of the two coefficients there. Okay, this coefficient change to 0.46, and this coefficient in the numerator, in the denominator, change to 0.0207. This is for iso heat flux. This equation for isothermal, that's for the Prandtl number outside this range, but it still has a limit. Okay, that's the product of the Reynolds number and the Prandtl number should be greater than 100 for this equation. Okay, so remember those limitations for each equation. So you have many equations for the same Nusselt number, so you have to know what do we need, right, for a particular problem. So let's look at a example 5.5, flat plate with constant heat flux condition. Okay. So what is the problem? It's a 1 kilowatt. Okay, so the total heat transfer into it is 1,000 watt. Okay, so it's a plate. Okay, again, the boundary layer, right? There was my joint. You have iso heat flux condition. Okay, to the flow from the left to the right. Okay, so heater is constructed of a glass plate with an electrical conducting film that produce a constant heat flux. Okay, the plate is 60 centimeter by 60 centimeter, so the area of the plate is 0.6 meter times 0.6 meter. So it's a square. It's a square plate down here. Okay, 60 centimeter for the side length. And place it in airstream, 27-degree air, 1 atm with velocity, free stream velocity, U infinite. U infinite is 5 meters per second. Okay. So calculate the average temperature difference along the plate. Average temperature difference and the temperature difference at the trailing edge at the end. Okay. Okay. See, for the iso heat flux problem, this is iso heat flux problem. So the goal is to calculate the average temperature. It said average temperature difference, but you know the T infinite is 27 degree. It doesn't change, right? Because outside the flow, it doesn't change temperature. So basically, it's just try to calculate what is the wall temperature, average wall temperature. Okay. So how do we start? With this type of problem, the first step is find the properties. Just like the previous problem, right? You find the properties. Where do you find property? You have those appendix, right? In this textbook, have the engineering tables. It show you most of the property. Okay. So, but for the boundary layer heat transfer problem, you actually have a problem. You need to know the temperature. You remember last time in the example 5.4, we define a film temperature, okay, with the film temperature, because you have to find the fluid property near the wall, right? In the near wall region, the fluid temperature inside this boundary layer, it's not equals to the free stream temperature. It does not equal to the wall temperature either. Is that right? So what is the temperature for this boundary layer? It's in between, right? In between the outside temperature and the wall temperature. Okay. So it will be smaller than the wall temperature, but it will be greater than the outside temperature. So that's why we use something called film temperature, right? Film temperature to find the property. But it's easy for the isothermal condition. You have a wall temperature, you have the outside temperature. So what? So then your film temperature basically is half of the wall temperature plus that's for the isothermal, right? For that example. Okay. But hey, for this problem, what is the film temperature? So what is the wall temperature basically? You don't know, right? The wall temperature is changing. It's iso heat flux. I only know that I have the power goes into this thing is 1,000 watts. So the heat flux is 1,000 divided by the area, right? That's heat flux. But we really don't know what's the wall temperature. It's changing. Okay, so what's the strategy? So if you see an iso heat flux problem, actually it's not really easy to do. Okay, so you have to, you see the question here is to find out what is the wall temperature, average wall temperature. But now before you know the wall temperature, how do you calculate the film temperature to estimate, to evaluate the set to find the properties? Okay, for iso heat flux problem, if you see it next time, you need the iteration. Okay, since you don't know the wall temperature, so first try, your film temperature, you can just simply use the outside temperature. The first try. Okay? You have no choice because that's the only temperature in this problem you have. So it is 27 degrees Celsius and 300 K. Okay, so 300 K. So then you can find your viscosity, okay, 300 K, your Prandtl number even, right? Okay, your K, thermal conductivity, everything you can find from the appendix, okay? And what else? Okay, I think that's what you need, right? Okay. Then what equation you're gonna use? Okay, I want to turn to the previous page. Not the previous page, maybe previous file. Okay, can you locate the equation that you need to use to find the average wall temperature? Mm? Anybody?
Equation 2 all the way at the bottom, the very
All the way
last.
to the bottom. Yes, you see it, right? That's what I thought. Heat flux condition. You have so many equations local. This is average. So 2 is average. So you see that, okay, it's down there. Okay. So let me write it down, that equation, to see, do I have everything else? Do I have everything in this equation to solve for average temperature? Seems like I do. Okay. So TW minus T infinite TW average, right? That's average temperature we want to calculate. So equals, okay, heat flux. You know what the heat flux is? Let's review it. What is heat flux?
Q over A.
Yeah, Q over A, exactly. Okay, did I copy it right? Is that equation? Let's double check it. Maybe after I check, I can memorize it. Reynolds number half, Prandtl number 1/3. Okay, Q times L divided by K. Okay, here it is. Coefficient 0.6795. Okay, my coefficient 0.6795. Okay, I write it right. I write it correctly. Okay, so in this subject heat transfer, you need to be really careful, even writing down the equation. Okay, do I know everything here? I think I do, right? The Q prime is what? Q prime is Q divided by A. So in this case is 1000 watt divided by 0.36 meter square. Is the textbook give me the answer for that? Q. No, it just did it directly putting onto the equation. Okay, it's the whole equation. Okay, but if you want to calculate, you can calculate. It's about less than 3,000 watt per meter square. Give me a value. Okay, you guys have the calculator, right?
I got 2,777.77.
Okay, let's say this 2,778 watt per meter square. Okay, I got one letter down. Okay, L is what? 0.6, right? Meter. K is our property. I think it's based on the temperature, 300 K of the film temperature. You got a K equals what, 0.02624. Watt meter C. Okay, so viscosity is 15.69 times to the 10 to the negative 6. So you should be able to find the Reynolds number. Reynolds number based on the Reynolds number equation is 1.91 times 10 to the 5. I know it's laminar boundary layer, still not reaching 5 by 10 turbulent yet. So everything we learn here is valid. Okay. So what else? Prandtl number. Prandtl number from the table is what? 0.708. Yeah, it's 0.71 basically, right? For air going through it. So I have everything. So my average T wall calculated from here is 267. 200 is that 267? Yes, 267 K. No, hold on. Yeah, 240, 267. No, I'm sorry, 240, I think, right? Is that 240 or 267? I think it's 260. Oh, okay. And it plus the ambient temperature. Okay, TW will be 240 plus 27 C. It's not K, I'm sorry. Okay. Because outside is 27 degrees, right? So TW will be 267. Okay. TW bar minus T infinity is 240. Okay. All right, everybody follow me? Still with me? Okay. But that's not the end of the story. Hey, look at this. This is just the first try. We are using iterative method. Okay, it's just first try because our starting point is wrong. I know my fume temperature is not 27 degrees, 300 K. Okay, I'm using the outside the flow temperature as my fume temperature. Now it seems like my wall temperature is so high, you know, and the outside is only 27. My fume temperature, it should be in between 27 and 267. Okay, average of that. So it's really not 300K. Okay, the property all has to be changed. So we're gonna have the second try. Okay, now you have a new fume temperature, which is what? Half of the 267 plus 27. Okay, so it is 147 degrees Celsius. Be careful, Celsius and Kelvin. And then you need to convert into Kelvin 420 to find those properties. 420. Okay, so now you see the property gonna be different. Okay, it's 300 degree K and a 420 K. The property probably for the air will be different. Okay, so now you're gonna find all those properties again. So the Q is still the same. The heat flux Q prime is still the same, right? Length is still the same. K will be different. Now the new K is 0.035. Okay, water meter C. Okay, and the Prandtl number. Okay, the Prandtl number will be 0.687. Okay, the viscosity also changes to 28. Previously it's 15.69, right? Now it becomes 28.22 times 10 to the negative 6 meter square per second. Okay, so Reynolds number therefore will be equals to Reynolds number L, the overall Reynolds number, right? Equal to 1.06 times 10 to the 5. Okay, so now your new TW average based on all those properties, based on the same equation here. Okay, then it become 243 degree plus 27 degrees. So it will become 270 degree C. Okay. Okay, this is the second try. Now you have a improved average temperature. Okay, but is this end? Do you need to do the third try? Since now you have a better TW, you can try it. I think you can put it into an Excel program. Okay, third try. But why I don't need to write it down the third try? And in the textbook, if you look at it, it doesn't have the third try either. Okay, so why don't we even need to bother to have the third try? Anybody can answer me?
Is it because of how close the answers were, or no?
Yes, it's how close the answer will be. Look at this. The second try, you start with a wall temperature 267. Okay, if you are starting the third try, then your fume temperature will be 270 plus 27 divided by 2 will be 140 what? 148.5? Right, 297, right? 297, yeah, divided by 2, 148.5. Okay, so so you have 1.5 degree temperature difference in the film temperature. If you look at your tables in the textbook, that won't show any difference in the K and the Prandtl number and the viscosity with 1 degree temperature difference.
Quick question, Dr. Zhang. Where are we looking in the textbook at these tables?
I think that's...
It's the appendix ones, or?
I think it's appendix. Let me see. Let me tell you exactly. I think appendix 8. Okay. Appendix 8 in the back of the textbook. It should have all the properties. See, I see it. You have so many properties. Just look into it. I have many tables. Depend on you have the solid or you have liquid, gas, and also property of the many different properties all in there. Okay. Property of air at the atmospheric temperature. I'm looking at the table A5. Okay. So that's for the air. Okay. For the liquid, it will be A4. Saturated liquid, right? Property A4, A5. Okay, and the property of air gas at the atmospheric pressure is A6. Okay, so you probably need to learn how to use those tables. Okay, that's a skill for the engineer. Engineer basically, field engineer is basically looking into all those tables, codes. Okay. Okay, did that answer your question?
Yes, sir.
Okay, and look at that table A5, if you have it. You see, they have the increment of 50 degree temperature for every other, every different property values. Okay, the increment is 100 degree. The table A5 start with 100 degree K. Okay, the next point is 150K, the next point is 200K, the next point is 250K. So the property, you don't see property, if your property change is less than 50 degree, probably you just pick one, okay? Or you interpolate it. If it's 25 degree in between, then you just interpolate it, right? Now for this, look at this. It's just 1 degree, 1.5 degree difference. I don't see you will have any different values, okay, for those property if the temperature is only 1.5 degree difference. Okay. Does that make sense? The first try to second try, like let's see what's the temperature difference. 300 degree K, right? See, now the 420, you have a 120 degree K difference. That's why you will have a new set of properties. Okay. If it's 1.5 degree difference, you won't have a new. So you will have the exactly same property. So you will have exactly same 210 to 70 degrees Celsius temperature calculated, every temperature. Okay. So that's why we don't need to go through the third iteration, but we know it's good enough. Okay, but sometimes we do. Sometimes if the temperature really is different, first try and the second try have like a 800 degree difference. Maybe the temperature you get it from the second try is still not good enough. Okay, it's too much difference. Then you're probably gonna go through the third try. or even more. Okay, is that clear to everybody?
Yes, sir. You just interpolated those values from the table. That's what you were saying. The Prenel's number and all that.
You don't even need 420. I think they doesn't have the exactly 420, right? If you don't have exactly 420, you interpolate it. They have a 400 degree and a 450, so you just interpolate it. Okay, but if it's 420 versus 421, I don't think you need to interpolate even. Just use the 420 value. Okay. Does that make sense? Everybody?
Kind of.
Okay. Want you to exactly with me. Okay. So, you know, you guys are 21st century engineer, right? You use computers. So this is really, really, I think it's a good candidate to write a like Excel program to do this iteration. Okay. Well, let's make it a project here. Okay, a small project. Let's say it's I don't want to be exactly same weight as the video project. Let's say half weight of the video project. I want you to actually create a Excel worksheet, spreadsheet to do the iteration. So do you know, you guys know how to use Excel, right? So you had a class at the beginning, engineering 109 or something like that, to learn how to use Excel, right?
Some people had it, but some people didn't. Like my
Okay.
engineering 101, it was kind of just a BS class, honestly.
Yeah, I know.
Like some people
I
do
agree. but doesn't matter if it's BS class. Then it's burdens on you to learn Excel. It's really important. At least Excel. I don't care about MATLAB. Okay, but at least for chemical engineer, for mechanical engineer, for any engineer, you really need to be good on Excel. Is that good? Is my statement correct?
No, yes, sir. Yes, sir. It's been really helpful in a lot of classes.
Yes, I think it's true. From my experience, so many years I'm working, you know, you don't have to know computer programming like C++ or even MATLAB. It's okay. If you don't have it, don't have it. But none of the engineers, zero of the engineers don't know how to fluently use Excel. If you don't know how to fluently use Excel, probably this is not your career. Okay, really, I'm serious. Okay, Excel is the basic. You have to play with data. So in Excel, if you're not good at it, that's the time for you to learn it and improve it. How about that? Okay, let's make a small project like this, half weight of the video project. Okay, so to create a Excel program, Excel can do iteration. So for example, you pull the entire row, you pull it down, it will calculate the same equations for you, right? With different input data. Is that right, guys? You know what I'm talking about? If you have an equation set it up, if you pull it down, right? You can do the same equation with this new data for the next row. So you can do the same calculation. So here it seems like this is a good candidate. See, you have one equation there. The equation never change. Okay, the equation never change. But okay, what happened to my screen? Okay, so the change is the input values. So I like you to make a small program, then it can implement this iteration. Now I do 2 iterations, it's okay. You know, I can do it by hand. Maybe you need 10 iterations to get a converged solution. So what, you're gonna calculate the 10 times? This is not good for field engineer to do this whole thing 10 times, right? You already know, see how many time we spend on here and just solving this, right? So having a Excel program in hand, it's good for you now and for the future. Maybe even you will do the heat transfer iso heat flux calculation like this. In the reality, iso heat flux is way more common than isothermal condition. So in practical applications, usually isothermal, iso heat flux. So iso heat flux, you have to do the iteration. So if you have a secret program like that in hand, maybe you will impress your boss. Hey, I can do it quickly. In a second, I found the result. Okay, I think it's good for you to practice that. So let's make it a small project, halfway the project, and to create a Excel program to do this iteration by just pulling down the row. If you pull down 10 rows, it will do 10 iterations for you. Okay. If you're pulling down 5 rows, it will do 5 iterations for you. Okay. So let's make a project. How about that? Okay. Yeah. Go ahead. Any questions?
When will it be due?
I'm open. How about 2 weeks? Or you want longer? It's fine. You know, I can even make it. Hey, oh no, you don't have many weeks left for the semester, right? Let's do 2 weeks, one today. How about that? And you see, there are some difficulties there. So if you can actually have the equation to implement the interpolation of the properties, that's good. So you can, in one of the worksheets, you can spreadsheet, you can write down, copy the tables, the appendix A5 for all those properties, increment by 50 degrees. So if you can automatically let your program interpolate, that would be good. So if you know, so when I grade it, I will look into that, see if you have the automations for the program. So if everything you have the hand input into your program in that spreadsheet, then you will still get good grades. But I will put maybe 1 out of 5 points is the difficulty, which include this automation, for the automation of the interpolation of the data points. Okay.
Can we do this in place of our next experiment? Since we have one due on Monday, can we use this one for our next one?
Okay, if everybody agreed. If you want to in place it, I can make it. Let's see, but I don't want to make this as the same weight as the video experiment. You spend a lot of time on those experiments. So this is maybe short. Still half weight. Okay, let's in place one experiment. So there will be one due Monday. Okay, the next one will be this. How about that? But I give you 1 week after next Monday to do this. So it's a half weight. It's half of the regular video experiment. How about that? How about that? But and you actually start today, from start today. So about 10 days, 11 days for the due. Let's do due on Monday. So next Monday will be the video experiment number 3. Then the following Monday will be this project.
And then the Monday after that, we'll have another video project. Is that correct?
Let's say the 2 weeks after that will be our next video project. We have probably 4 weeks left. So 1, 2, 3, 4, right? So I guess.
It would be our video project due the 16th, this project due the 23rd, and then the next project 7th of December.
Yeah, then the last project, probably that will be the last project will be due on the early December.
So you said like you just want it for air, so we can just take that whole A5 table and just bring that over, and then you just want
you want to be, you know, if you want to do to achieve that 1 point bonus, 1 point out of the 5 points for the difficulty. If you want to achieve that point, you better input that table, the value, hand input the value into the spreadsheet as a separate spreadsheet. Okay, then your program spreadsheet will read that data and do some interpolation.
Okay, so we can because I was noticing that on like the table 5, like how it stays like the same for some like the Prenodes numbers. It's just like 0.60. It's just 0.68. So would we, like, if it's in that range, just stay there, or would you want us to do like a big formula for the Prenodes number where it's like an average, like the like a linear
interpolation? Do you know what I mean by interpolation?
Yeah.
Okay.
Yeah.
Linear interpolation is sufficient. Okay, that's the easiest interpolation, right? I don't want you to go to some fancy interpolation. Just the basic interpolation is so-called linear interpolation, right? If it's in the middle, it's just half between the 2 points. Okay, if it's 1/3, it's like 30% of
Well, no,
that.
yeah, that's what I mean. Like if you look at the table for if you go from 500 degrees Kelvin all the way up to 600 degrees Kelvin, it's the same Prenold's number.
Okay.
It doesn't change.
So that's why I say you do the interpolation by program. It's not for hand interpolation. So you give it an equation, it will do the same thing. If you give it two same number, it will give you two same number for the interpolation in between, right? So that's called linear interpolation. You want to implement that into the program. Okay.
Can you post the table to the group me so we all have it?
Okay, let me take a picture. How about that? Okay.
And you want the project based directly off of this problem?
Yeah, based direct off this problem, but you can apply. You see that's a program. That's good thing about program. Then you can, if you have other problem, you can have different input values. Like
Well, I only ask because the area for this one is for a square, so the area would change if it's a different problem.
So how about in your program, you can actually input the area as a variable input. You say area. I have my area right in one of the column. Area is this, length is this, width is this. So in other application, if you in the work you want to use, you can just change the dimension for the area. It will automatically calculate in your program. You see my point?
Okay.
Everything you know, that's my hint to you, my trick to you. So when you do programming, this is kind of like a programming, although it's just Excel, right? But kind of like programming. So in all the programming process, you give variables, you give a column or basically maybe a box, just say this is for the area, okay? Area. And maybe just for the length and the width, you can just have the input value as the length and the width. Then let the program and read that value. So next time you apply this to another project, you can just change the length and width. The program will automatically taking care of the new dimension. You see my point?
Yes, sir. I understand. I was just asking
to
be sure.
Yeah, I just really want to make it to benefit you in the future. If you have the skill like this in the future, you will be good. You know, when you do the real job, and I think they will be beneficial. Okay. Okay, let me take a picture. I have a little bit dark background here. Okay, good. Okay, let me post it in the group me in case you don't have that textbook. I'm looking at, this is a table A5. Okay. I think that should be good for this project as a property. Let's see, they have the viscosity, K, Prandtl number. That's it. That's all you need, right? So yeah, that should be good. Enough information on it. Can you see it clearly? I think, yeah, it's pretty clear, right? You have the hand input, manually input some of these properties into your program, I guess. Then let the program automatically read it, and that would be great. Okay, but if you want to lower difficulty, it's okay. Still, I will give you points. Okay. Okay. Do I still have time? I have 10 minutes. Let's do another example. Okay. This is for the ISO heat flux conditions. Okay. Then the next section, 5.7 in the textbook, talks about the friction. Okay. Okay. Oh, okay. Before that, we have one more example to give. The example 5.7. Okay. Let's do 5.7. I think I have enough. 5 minutes 10 minutes should be good. 5.7, it said this, engine oil 20 degrees Celsius is forced over a 20 by 20 engine oil. Okay. This is oil. This dimension is 20 centimeter by 20 centimeter. It's also a square, okay? The velocity U infinite is 1.2 meter per second. Okay, the place is heated with uniform temperature. Okay, that's an easy one. 60 degrees Celsius. Okay, T-wall, constant T-wall. So isothermal condition, which is easier in calculation, right? The calculate the total heat loss by the plate. Total heat loss. Okay. So how do we do it? We have a bunch of many equations. So Q. So Q is what? Write it down. Then they tell you what to do, right? T wall minus T infinite. Okay. Do I have the T infinite? 20 degree. Okay. Okay, 20 degrees C. Okay, good. So I have T wall. I have T infinite. Do I have area? 0.4 by 0.2 by 0.2, right? So it's 0.04 meters square. Okay. Oh, do I know H? Okay, I don't know H. So I need a overall average H. Okay. So I will start from what? Average Nusselt number, right? Okay, for this. Okay. So, okay, now we have a little problem here. Okay, let's see let's check the Prandtl number for this problem. Okay, so let's say, because Nusselt number, we know we have a couple equations, but one equation has a range, right? You know, the general equation previously I gave for the isothermal has the range for the Reynolds, for the Nusselt Prandtl number from 0.2 to, do I still have that page here? Yeah, you see, if the Prandtl number is outside this range, probably that's the only equation you're gonna take, okay? Not much else you can do. So let's check my Prandtl number for this. So the Prandtl number for this case is what? So in order to get the Prandtl number, we need to do the film temperature, right? Film temperature is half at the T wall plus T infinite. So in this case, pretty straightforward. It's isothermal, right? 60, 20. So the average is 40 degrees. That's our film temperature. So based on the film temperature here, I think they get a Prandtl number. Okay, 2870. Wow. Okay, 2870. That's probably too big for the isothermal equations. So we have to use that equation. So we have to use that equation. Equation 5.51, right? It's a long equation, long version. So okay, so we use the total length to get average Nusselt number. So Reynolds number length half times Prandtl number 1/3 divided by 1 plus 0.0468 over Prandtl number over 2/3. That's terrible equation, too long. Okay, but hey, we have to be patient, right? That's what we get paid for. Okay, so for that, the Nusselt number is calculated as okay, this is not average actually. Okay, I follow the book. So this is still local. Okay, local X. Okay, the average is just 2 times. Okay, hold on. The Reynolds number at the end of the plate, 152. No, not the Reynolds number, the Nusselt number, 152.2. Okay, do I have another page? Yes. Okay, so remember, when we talk about this equation, we talk about the coefficient. So this is the isothermal condition. So we use the original equation, okay? If it's iso heat flux, then the coefficient change. So in this case, we don't need to change the coefficient, okay? So what's next? H equals to your Nusselt number at the end times the K divided by X, the length, right? So 152.2 times 0.144, which is the property, right? at least this problem, film temperature is certain, so we don't need to iterate, right? Sometimes you will see very complicated problem. So your heat transfer coefficient at the end of the plate is 219 times 2 watt meter square C. Okay, so you gotta find the average. Oh no, I'm sorry, 109. I look at the wrong lines. 109.6 watt meter square C. Okay, for this special condition, there's one more equation. I think I didn't give you. The average heat transfer coefficient equals the heat transfer coefficient at the end multiplied by 2. Okay, so it's 2 times. This is from empirical, it's an empirical solution from experiments. So in this case, so the average heat transfer coefficient will be 219.2 meter square per watt meter square per C. Oh, I'm sorry, watt per meter square C. Write it wrong on the unit. Okay, so now you have the average heat transfer coefficient. How long time? How many? I have 3 minutes. Okay, so the overall heat transfer rate will be your average heat transfer coefficient times area, now times the temperature difference, TW minus T infinite. So 219.2 times 0.04 meter square, okay, 0.2 by 0.2, all right, times, what is the temperature difference? 60 and the 20, okay, so it will be 40-degree difference, okay, so total heat loss, heat transfer to this is 350.6 watt, okay. So this is the total heat transfer. So this is the problem with, so that's why in the beginning of any problem like this heat transfer, you probably want to check with the film temperature. Okay, first thing, always the first step, as I mentioned in this problem, the first step is to find the properties. Okay, property is not that straightforward to find. Okay, so you need to get the film temperature. If you have film temperature, that's good. Then you can directly find out those properties needed. K, viscosity, you need the K and viscosity. I skipped it here, but you need the K, you need the viscosity, right? Okay, for the calculation. So the Prandtl number also is one of the property you need. Okay, so in this case, after you look at the Prandtl number 2870, you need to be very sensitive on the Prandtl number. Okay, that's a big Prandtl number, too big. Okay, too big, then I cannot use the equation initially proposed. Then we have to use the alternative equations, which is this. Okay, in this alternative equation, since we don't have much of the theory, this is the equation for local Nusselt number. So you use at the end of the plate to calculate the local Nusselt number and the local heat transfer coefficient. Okay, and with that one, multiply by 2, that will be your averaged heat transfer coefficient. Then you can calculate the heat transfer rate total. Okay, is that good? I have 1 minute. I can entertain one question maybe. So now, most of you, many of you in my fluid class too, right? Fluid heat transfer, we teach at the same time. Now you see the difference between fluids and heat transfer. Heat transfer is a more complicated subject. Then we basically don't have much of the theories, calculation, like a dissolving differential equation, whatever. And ended up, it's too difficult. Then it becomes, you just apply equations. People finding all those equations from experiment, from empirical solutions, from everywhere. So you get those lot of equations, then you apply those equations to solve actually practical problem. It doesn't need to solve differential equation much, I guess. Okay, it's a little bit different approach than fluid. Fluid is more, I think it's around theory a little bit more. Okay, around the mathematic calculus a little bit more than this. But here, the difficult part is you have so many equations, very tedious process. Then you have to identify the correct equation for different conditions, okay? Then and do some calculations. The calculation even could be rather complicated. Sometimes you need an iteration even, right, in the previous problem. Okay, that good? Okay, if you have no question, that's it for today. Okay, so see you on Friday. Have a good day.
You too, sir.
Okay.